Okay, so I'll start recording. There's a part in a bit where I'm gonna pause recording because I'm gonna talk about homework groups for the videos. But to start off with announcements, there's a math colloquium happening tomorrow. Let me pull it up. Um, a guy from UC Berkeley is gonna give a talk tomorrow at 1:30 on asymptotic dimension. So what does it mean for a Euclidean plane to be two-dimensional? Why do we say that that is? So if you're interested in something like that, that's tomorrow at 1:30 upstairs in Galileo 202. So that's not the big lecture hall in 201, it's the one right next door. So that's happening. There's also a tech club meeting tonight at 5:30, and there will be pizza. I have ordered the pizza. And the goal for that, do you want to give a pitch about that?
Uh, yeah, since the first meeting of the semester, we're just going to mess around with the code and give a basic intro to what to be. You have like other ideas for the future, like maybe a hackathon, probably a bit ambitious, but we will not this semester, if not this semester, next semester.
Yeah, cool. So lead code today, plans for the rest of the semester, working on a hackathon, maybe collaborating with the data science club. So yeah, should be fun. And there's pizza. So homework 2, which is the math packet, that's due on Thursday, next class. If you have it ready now, I'll take it today. You can put it on the table as you leave, and that's fine. Or if you want more time to work on it, hang on to it. That's up to you. Homework 3, which is the algorithm analysis, that's due the following Thursday. So next Thursday, the 6th. And then what I'm calling video 1, the data structures video, is going to be provisionally due March 13th at the moment. As we get closer to that, if a majority of the class wants more time, I can hear arguments. But I needed a date, so that's the date that we've got for now. Okay, so for today, in a bit, I'm gonna stop recording on Zoom and then I'll talk to you. Here are your groups and here is your topic. We'll just go over the assignment again. So now that you've maybe had time to sit with it, I'll touch on the main parts. An addition is I've posted the rubric as well, and the rubric includes like a collaboration metric. And so there's going to be a Google form that you fill out to rate your collaboration with your group. We'll also probably have a discussion board for the video. The idea is I want to like post, here's the links to your classmates' videos, and then you watch them and leave a comment on X number of them. So I'm not too sure about that yet. So you might see something on Canvas of like, hey, you've got a new thing to do. I haven't done this before, so I'm gonna test it out. So feel free to ignore that if you see it on Canvas until I tell you it's ready. So first bit is looking at the video assignment. Second bit is actually going over the data structures. And then the last 10 minutes or so, I'll have time for you to actually get into your groups, share names, contact information, all that fun stuff. And so you can set up a time to meet and start working on the assignment outside of class. Any questions or concerns before we get started? Great, let's do it. Pause recording. Okay, so I've fixed all of the known typos in the video assignment. So just to go over it again, now you know your groups and you know your topic. And so you'll make a video explaining your topic and upload it to YouTube and submit the link. You also need to write code to implement that structure. And so you'll submit the code in some way. So either you zip everything and then turn it into Canvas, or if the code is original, then you can upload it to GitHub and then give me a GitHub link and I'll give you 5 points extra credit. And then after that stuff is submitted, every group member just needs to fill out the feedback form. And that's who are you? What's the video? Right now there's only one. And then which group are you part of? And then rate, did you work well together? Did you talk to each other? Was the work share roughly equal? And then just write any comments that you have about how your group worked. No one else in your group is going to see this, only I'm going to see this. So please be honest. And this will help me make a decision for the rubric. Do I have the rubric up? I do now. The rubric is now on Canvas, which is just like, do you understand what's going on? Did you implement it well? Does the video look good? Did you work well together? That's the part that the Google form is going to help me with. And then, is it creative? Is it engaging? So the rubric's there. So the idea for grading is I'll print these out and then I'll watch your video and circle things and then hand it to you. Okay, that's the rubric. And again, so I've broken the video task down into like 3 separate roles, but you can feel free to ignore that if that doesn't make sense to you. I want you to be able to illustrate, here's how this works with simple examples, and explain the efficiency as well. I want you to implement something in code to show how your data structure works with some non-trivial data. So the architect has some toy examples, some easy things. Non-trivial is something more complicated. And then implement it. And again, you don't necessarily need to come up with all the code yourself, but if you do, then you get more points. You just have to cite any sources that you use and adapt it to your situation. And when I say cite sources, you have to put it in comments in the code and also say so on camera. And that includes any code that AI may write. And then just again, to mention, if you didn't write, so if you choose the route where you don't write the majority of the code, then you can't get those points on GitHub. You just zip it and turn it into Canvas. And then the video side is to do the explanation from the architect of here's how this works. Voiceover, briefly scroll through the code, say are these functions. And this is what it looks like when it processes the data. And then edit and post it. So the videographer, in this envisioning, the videographer is responsible for turning everything in. But then every member of the group also has to fill out the Google form. And I went over the notes last time, so I'll leave that. You can read those again if you want. So I've assigned you, here's the data structures for your group. If you want to do a different data structure, feel free, just talk about it with your group and then let me know. Because there's 10 groups and so there's multiple coverage of each of the data structures. So I'm happy if you want to try something else. Okay, that's the video. Any questions? Cool. I hope it's fun. I hope it's a new, interesting kind of assignment. All right. Now for the data structures. All right, so for this one, so we've got the packet. It's going to be a little bit different now that we're getting into the video topics, where I'm going to have like an overview of here's how the data structure works. And then after we go through this slide deck, my plan is we have packet problems that we just like, we'll spend the class time in future days working on this until we're done with it, and then we'll move on to sorting. So the packet is more like fun, interesting problems that we can work on together instead of more of like the toy examples that they've been in the past. Okay, so that's basically what this says. So once we talk about the data structures, then it'll be roughly packet time and work with your groups, like extended office hours. That's my plan for the class. Okay, so what's a data structure? A data structure is something that holds data in a certain way, and the structure really depends on what kind of data we have and how exactly we want to access it. So it depends on the kind of data that we're working with. The ones we're going to go over are contiguous and linked structures. We're going to talk about stacks and queues. These first two, I expect you have heard before, probably from 222 or otherwise. We'll talk about dictionaries. I think I mentioned last time, I don't really like the way that the textbook lays out dictionaries. I think it's a little bit confusing. So for the video, I'm kind of combining dictionaries and hashing for you to implement as you see fit. But then the other two are binary search trees and priority queues, which you probably have heard of binary search trees before, maybe not priority queues, maybe, or maybe not hashing. So the goal is that they should be a little bit familiar. Okay, so for contiguous structures, contiguous meaning that something shares a common border or is touching, they're next or together in sequence. This is definitions from Google. Synonyms being like adjacent or touching. So we can have property that is contiguous. So A and B are right next to each other. You can also have the contiguous United States, which all the states share borders. So that's the definition of the contiguous states. So they're all together. And the main type of contiguous data structure that we know of is an array, where we've got all this data, it's together in a line. Arrays are typically implemented as fixed size in memory. So once we make, you see this in like Java or C, C++ type things. Python kind of glosses over it for you. But the idea is that arrays are fixed size. So once you create an array, you say, here's how big I want it to be, and then it doesn't change. If you want something that's bigger, then you need to make a new array that's bigger and reallocate. So copy all the old things over to the new things. So fixed size. Elements are typically located by their index or address. So like here, we've got our elements inside the boxes, and we access them by the index, which typically starts at 0 and counts up until the size of the array, -1. So if we've got 6 things in our array, we count indices starting from 0 up to 5. This should not be new. Typically, it kind of depends on the programming language, but typically arrays live all together in memory. So that's kind of why they're fixed size, because the programming language the compiler can be like, okay, you want an array of X size, I'm going to reserve that block of memory for you. And that's why if you are like, can I have one more space? It's like, no, I reserved this amount for you. If you want bigger, you got to go reserve another. Some programming languages like Python give you dynamic arrays, or in Java, there's like the lists API. And so those allow for automatic resizing. So it takes care of that for you. again, this should all be familiar, this kind of way of we're visualizing an array. This, as we go, I'll note that I have a lot of, like, I'll explain, here's what we're talking about, and then I have a bunch of pictures. If you want to, like, recreate this kind of picture, if you were assigned an array, be like, here's how you insert something into an array, and you like draw the one here. And we say, here's how we access something. And so you'd say like array square bracket at index 0. You're familiar with one-dimensional arrays. You may also be familiar with two-dimensional arrays, which is how we can represent a matrix, where we've got rows and columns, where the first number, when we say array at x, y, x is typically the number of rows, y is typically the columns. You can also have three-dimensional arrays. Again, depends on your data format, but it's possible. And this can keep going for however many dimensions as you need. In terms of operations, it's O of n to search through an array because, well, I'll put an asterisk here. In what cases would it be O of n to search through an array for something? Yeah, if it's not sorted, then you've got to start at the beginning and look through everything. And the worst case is that it's all the way at the end. What other conditions could search not be O of n? Yeah. 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 So, and binary search is, yeah. Yeah. So take the middle, look left or right. What's the complexity of that? Log n. Yeah. So n or log n, depending on how you set it up. And so if you decide that I'm working with a sorted array, then that affects how you insert and delete as well. Or maybe not delete, but definitely insert. For access lookup, typically we consider this to be O of 1, because if we know where the memory address is, we can just add some value based on the index. So if I know here's where the array starts and I'm looking for the third element, I just add 3 and that gives me that item. So access lookup is typically constant time. Delete for similar reasons. Again, whether it's sorted or unsorted, maybe log n as well. But if it's unsorted, then you've got to go through the whole thing and search for the thing that you're going to delete. If it's sorted, you can do a binary search and then just delete when you find it. Other operations that you can think of? These are pretty much the main ones that we care about. Typically for data structures, we're looking at how do you insert something? How do you remove something? I don't know, maybe sort could be an operation for a list. And again, you've probably seen that the complexity of sorting algorithms can vary. So depending on which algorithm you choose. But these are the main ones. So another kind of list like this is a linked list. So a linked structure. These are, by contrast, they're not contiguous in memory. So whereas arrays are like, I've reserved this spot and n spots down the line, linked structures aren't contiguous in memory. Instead, they're joined by pointers. So I've got this spot in memory that points to another spot in memory that points to another spot in memory over here. So they're joined by pointers, and each of these structures, these nodes, holds some piece of data. So you'll see, basically we represent nodes as like a box with some piece of data in it. and there's a pointer pointing to another node somewhere else. And so this is a visualization of like an array has this amount of space reserved, whereas a linked list kind of goes all over the place. And it can vary whether we decide, do we want our linked list to only have a next pointer? Do we only want one, as in this case? Or do we want 2 pointers? Do we want to have a link going the other way as well? It depends on what you're trying to implement. So I would recommend, as you approach your data structure, try to consider, do I want to store this as an array or a linked list or some other foundational data structure? Okay, so 2 options or more. We could have more pointers if we want to. There's nothing restricting us. We can have as many as we want. We're the designers here. With linked lists, so arrays kind of help us do things that are more linear. So like a hash table or a stack or a queue. Linked list helps us to do things that may not be as linear. So like a graph can be really well represented by a linked list, or a tree as well. But graphs could also be represented by like what we call an adjacency matrix, which is basically like a 2D array, saying this for each row represents a vertex and each column represents a vertex. And so say this vertex is adjacent to this other vertex. And so it can go either way. So you've got choices for how you want to use these foundational data structures to implement other data structures, but we have to start somewhere. So for linked list operations, again, depends on kind of how we set this up. For search, if we start at the beginning and we go through and we take the next nodes all the way down, then that's O of n for searching. If we want to start somewhere at the middle, we probably need to have a pointer to that node to like hold it. So like, well, this has an even number. So maybe if we start here, if we have a pointer here, then we can, and if we've got left and right, then we can go left and right and do binary search that way. But if we don't have a pointer here, then we would have to start at somewhere where we have an anchor. So the head or the tail, the beginning or the end of the list. So those choices that you make can greatly affect the efficiency of the different algorithms. But typically search is O of n at the worst case. Accessing similarly, since we don't have availability to do like indices like an array does, then we have to start counting and go through each item till we find it. Insert also kind of depends. So if we have our pointer to the head node, the first thing in the list, then inserting at the beginning of the list is constant time because we know where that is. And so it's just a matter of setting up the links and we're good to go. At the end, if we've got a tail marker, then it's similarly. So we know where tail is. We'll just set the new node up there. Anywhere else in the middle is typically linear. But again, this matters. It matters for how you set it up. And then delete is similar. So we have to go through and find the thing that we want to delete. Okay, so that's linked lists. Any questions on linked lists or arrays? Okay, if you're extremely confused about linked lists, either from this class or from a former class, come talk to me. Because it's an important data structure and we need to be sure that like you know what's going on. So if it's confusing, come talk with me or ask your classmates. Okay, stacks and queues. Stacks and queues are what we call containers. I mean, they're all kind of containers. But these are containers that store the data in a particular order. And the retrieval depends on the order that you inserted things in. Stacks and queues are typically implemented by like arrays or linked lists. But these are more of abstract data structures where now we're getting into something that like we make up. I'm going to have a stack and this is how it works. And then I'm going to implement it using the like an array or a linked list. So this is an abstract data type. So stacks and queues are either first in, first out, or last in, first out. Again, this hopefully shouldn't be new. Where it depends on what order you put something in, that influences what you get out. So this is a stack where typically it's like a long rectangle with no top, and you can push something in and it stays at the bottom, and then when you push something else in, it goes on top of the thing that you just inserted. And then that keeps going until when you decide it's time to remove something, then only the thing that's most recently on top gets removed and returned. So the operations here are push, which is insertion, and pop, which is removal. There's also a queue in which the operations are enqueue, on queue to insert. So someone enters the line, and then dequeue, which is removal. So someone is out of the line. And so for queue, typically we represent there's the front of the line or the head of the line. The person who's like, if you're at the bank or something, that's the person who's going to be served next. And then the back of the line is the person who just got here, who's joining the back of the line. You'll also see queues in like computer networks and stuff, where there's some queue which represents here's how many packets of information that I can contain. And so packets arrives and it gets assigned to a buffer space. And then once we can transmit a new packet, then it gets dequeued, removed, and then sent on its way. Sometimes the queue is full, so there's no free buffers. And then the thing that was going to be enqueued is now just dropped. I got this from Roblox, so if you're interested in Roblox, they also have this notion of queues, so it can show up anywhere. Okay, for stacks, typically push is constant time, pop is also constant time. You can also access, like looking only at the top, also sometimes called peek, which is also constant time. Though that sounds great. We love constant time things. The only downside is that typically things that are, quote, not allowed are something like searching and lookup. Lookup is kind of together with searching, like being able to go through the things in our stack and see what we've got here. Those are typically, in quotes, not allowed. And they're in quotes because sometimes the way you implement it can make those possible. But at the basics, the basic operations are constant time. Push, pop, and peek. Similarly, for a queue, enqueue is typically constant time because we know where the back of the line is, so we'll just put the new thing there. Dequeue is also constant time because we know where the front of the line is, so just remove that. And that's also got the same quote unquote not things that aren't allowed as stacks. Double-ended queues, decks are also an option where you could like add and remove from both sides of the line. just depends on the type of data you're working with and what you want this data structure to do. Any questions so far? Okay. So dictionaries are a kind of data structure which goes together with hashing, where we've got this notion of key value pairs. So we've got some key that is associated with a value. So a key value pair. You may be familiar with the actual dictionary. So we've got some key, which is maybe the word itself, and then the value is the definition. So I can look up abandon, and that's the key. And then the value is give up without intent to reclaim, or the alternative definitions. So key value pairs. You may be familiar with those in Python, where we have curly brackets and some sort of what we call hashable type in the key. So that's the first thing, and then colon, and then on the right-hand side is the value. So in this, it looks like maybe ages or something, or maybe ID numbers, where some name is associated with a number. In the assignment code that I had, I've got a dictionary where as I'm doing this calculation, I'm assigning the group number to here's the topic that you're doing. So I'm using the dictionary that way, and then I just say because I'm going to store it, and so now I'm going to print here's the group ID and the value, which is your assigned topic. This example is where they're representing there's this passage and they've assigned each word or punctuation mark to be a number, and then they represent it in binary. You could also represent like the count of amount of times that this thing happens. So like bells happens 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And so you could represent bells with the value 11 to represent here's how many times it showed up in this passage. So key value pairs, that's the idea. So the main operations for a dictionary are search. So if I'm given some key, then I want to find the value associated with it. There's insert. So if I have some data X, I want to add it to the dictionary. Maybe you give X and the key as well. And then delete, which is if I know what I want to delete, go through and remove it. I don't have the complexities listed here because it varies. So dictionaries can be combined. I have the complexities here, but we'll talk about this first, where dictionaries can be combined with priority queues, where if you want priority queues being, I have a queue with some added ability to know what comes, like what's next. And so if I have like a max or a min for the largest or smallest key, I can combine this with priority queue, or predecessor successor. So if I'm given, if I want to get, hey, what's the next item in my dictionary, for like the successor, if we're have things in sorted order. In terms of how we implement it, again, there's difference for, are we using a sorted array? Are we using a linked list? So if it's unsorted array, searching is linear. If it's sorted, then it's log n. Whoops. For inserting, typically we'll like add 1 to the space that we're given and then copy the item. So if it's unsorted, then we don't care about where we put it. We'll just stick it at the end, and that's constant time. But if it's sorted, then we care about where we put it, and so then we need to put it in the correct spot. Again, for delete, if it's unsorted, see, this is what I don't really like about this explanation. So if it's an unsorted array, this is assuming that we have like a direct pointer to the item that we're going to delete. And yeah, this is kind of where I got sidetracked, which is why I've combined it with hashing, where the way that the textbook explains this, I'm not a big fan of. So yeah, so this is like 1/2 of this item, where the idea for dictionary is key value pairs. That's what I want you to take away with this. Of how do you implement a structure that represents these sets of pairs like this? The other thing that the textbook has a table of if you choose to implement a dictionary with a singly linked list versus a doubly linked list, the complexity also varies depending on what you're trying to do. So if you use a doubly linked sorted list, then these operations all become constant time, which is great. But for the others, it depends. Okay, questions on dictionaries before we move on? Okay, as we go, as you start working on your videos, if you've got major questions of like, I really don't understand what's going on, feel free to bring it to me and I'm happy to go over it again in class. Because again, your group's not going to be the only one talking about this topic. Okay, so binary search trees, which again, hopefully shouldn't be new, but if it is, then that's okay. Binary search trees, the main idea is fast searching. We can go through a binary search tree really quickly to find what we're looking for. And it lets us do some flexible updates. The idea is we've got a root which holds the top of the tree, or if the root's empty, then we don't have a tree. And then we've got children, which are the nodes that are positioned below. We can say a subtree is the binary search tree that starts from this node. And we say the BST property, the binary search tree property, this is the important bit, where for any node in our tree, all of the left children of this node are going to be less than the thing in this node. Anything to the right of this node is going to be greater. So left is less, right is greater. So let's look at some examples. So here's a binary search tree where our root is 8. And so everything in the left subtree is less than 8. So 1 is less than 8, 3, 6, 4, and 7. All of those values are less than 8. And then 10, 13, and 14, those are all greater than 8. So those are on the right subtree. And the idea is as we insert and delete things, that this property is maintained. So we have to be careful about how we insert and delete things. This shows like the top thing is the root, and then we've got the left subtree and the right subtree. There's the left child and the right child. And this is one of those structures that's recursive. So as we go down, maybe we go down to 2. This is the root of a new subtree. And so we've got a left child and a right child. Here's another one which shows that like 5 is a subtree, 12 is a subtree, is the root of its own subtree. And this property is maintained as we go throughout the tree. If the property is violated, if we find something that is greater, if we find something on the left-hand side that's greater, or find something on the right-hand side that's less, then it's not a binary search tree anymore. It would just be a binary tree. Binary tree meaning each node only has at most 2 children. So this is also technically a binary tree. This is not a binary tree. So again, and this is where like you can, so I'm telling you, here's the basic version of these things. You can extend it as you see fit. So let's say you have some way of storing numbers or keys, some kind of data that you need to be able to search through easily. But you want it to be associated with a value in some other structure. You can combine them. Or you can like attach, here's some data, or if this is a key, maybe you attach a value to this node. If you define what a node looks like, this can be your structure. So the idea is we're going to give you the bare bones idea, but as you go out into the world and make all these cool data structures, you can come up with what you need for the problem. That's something that I'm doing for a research problem I'm working on. I'm looking at like a specific kind of graph, and I'm kind of making up of like, I want a graph that represents this, this, and this, and no one's made that before. And so I'm deciding what I want it to look like, what sort of data I want to attach to it. So there's options. You're the designer. Let's see. So we've got the root of the tree, edges of the tree, parents and child, the terminology we use. The ones at the bottom that don't have any children, those are called leaf nodes. The idea is, well, there's no leaves on this tree. But if there were leaves on that tree, like the leaf is where the tree ends. Like there's no more branches after that. And then we also have the notion of the height of a tree. And that is how many levels. So like the root is one level, the root's children is another level, and another. So this is 1, 2, 3, 4, 5 levels. So we would say the height is 5. We can traverse the tree. So that is, if we're given the root, we can go around and see what's in this tree. This is unlike stacks and queues where we just know what's the beginning, what's the end, or for a stack, what's at the top. For trees, we can go through it and see here's everything that's in there. In order traversal, the idea is you start at the top and you trace kind of like, you know, when you go and like trace your hand for like the Thanksgiving turkey drawings, you kind of do that for a tree. And as you go around, depending on the kind of traversal, you write down the item at a certain point. So for in order, as I'm going around, in order, I write it when I'm at the bottom of the node. So now here I'm at 1, so I can write 1 and trace it around. Now I'm at the bottom of 2, so I can write 2. Now I'm at the bottom of 3, so I can write 3. And we keep on going. Now I'm at the bottom of 4, and so on. And so in order traversal gives you this sorted representation of your data. The pre-order is we're still doing that Thanksgiving turkey tracing, except we write it down when we're on the left side of the node. And so if we do this, first we're at 1, so we write down 1. And then we keep going. We're on the left side of 2, so we'll write 2. And we'll go over here and say 4. Note that this is not a binary search tree. It's just a binary tree. And the way I can tell that is 4 is to the left of 2, but it's not less than 2. So it's just a binary tree and not a binary search tree. And so in the pre-order, once we go kind of under 2, we don't write it down because we've already gotten it. But when we get to the left of 5, then we write it down. And it keeps on going where then we'll write 3, then we'll write 6, and then we're done. So that's pre-order. Post order is when we write it when we're on the right-hand side of the tree. And the difference between pre-order, post order, and in order is typically if you write a recursive function, it's just a matter of in which order the lines are. So yeah, so the idea is as we trace around, when we get to the right-hand side, then we write that item. For binary search trees, the efficiency of search is O of H, where H is the height of the tree. And traversal is obviously linear because you're going to list all of the things in the tree. So if you have n things, then you're going to visit n nodes. So that one's linear, but the rest are all a factor of the height of the tree. I think for those of you who are assigned to binary search tree, I think you can just choose one of the traversal operations and go with that. Just to show that you understand how that one works. But yeah, so insertion and deletion are all a factor of how tall the tree is. So it's not necessarily a factor of how many things are there, just how tall is the tree. And so that tells us that the balance of the tree is important. I was writing this slide and I'm like, it needs a Star Wars reference. So there's my Star Wars reference. And so this means that the order that you insert things matters. Because if you have a tree that starts with that you insert 4 first, that's all well and good. Because then that leaves you a tree that has height 3. And so that's fine. That it's relatively what we would say balanced. But if you start with 1 and you're inserting things in increasing order, then you get a tree which has a height of n and is not balanced at all. So the order which you insert things matters. Yeah, and you can combine this with other structures. So like I said, like if you have each node be the key, the thing you're searching for, then you can kind of attach the value to it. Or anything like that. So you can use pointers, or maybe you have some reference like the value for this thing lives over here. So it depends. You can set it up however you like. There's options. Any questions on binary search trees? I will mention that insertion or deletion. So insertion is fairly easy where like you start with the root, like let's say we're going to insert, I don't know, let's say 7, where you started the root and then 7 is greater than 4. So you go to the right subtree and then 7 is greater than 5. So you go to the right again. And again with 6, you go to the right and then not there, so you add it. Insertion is fairly easy. Deletion is a little bit tricky, where if I want to delete, so if I want to delete 1, then that's fine, because nothing depends on 1. So I can just delete it like that. But if I did have 1 and I want to delete 2, then it's a little bit tricky, where I need to go find the successor of 2. So the next smallest, biggest thing, which ends up being 3. And then 3 ends up replacing 2. So that's something that if you're assigned to a binary search tree, just make sure you understand. There's some dangers of doing this haphazardly, where you can end up with a structure that is not in fact a binary search tree. So just be careful about that. Okay. Next up is priority queues. So if we know what a queue is, a priority queue is just a queue with some added functionality. So a priority queue allows us for processing things in some specific order. So let's say I've got all of my tasks to do, and I'm going to prioritize the ones, if we do like earliest deadline first. Let's say I'm prepping for class this morning, I'm going to choose the ones for the graph theory class first, because that's coming up first. Even if even if my to-do list has all of these like things that aren't urgent, I'm going to take the urgent things and move them up to the front of the line. That's the idea of a priority queue, of knowing what's my structure and what's the next most urgent thing that I need to process. So we can have the case where new things can come in and maybe they're less important. So like someone sends me an email and, oh, I've got to get back to that, but I don't have to do that right now. So, okay, I'm going to do that later. Or something can come in and it's really, really urgent. And I'm like, okay, I have to drop everything that I was doing and do this right now. These are things that happen in everyday life that we're trying to model with a priority queue. So an analogy is like if you're at the emergency room and if you've just got like a scratch on your arm, someone who is more grievously wounded would need to preempt you in line because their situation is more serious. A way that you can think about it is if you've got some data and some priority, then maybe when you enqueue it, then you can add it. Maybe you can sort it where it's supposed to go, or maybe you can just shove it in there and then run through and look for the highest priority whenever you're looking to dequeue something. There's options. And so the idea here is that if we're enqueuing B2, here it just sticks it in between C and A. And yeah, so it preempts C when it gets inserted. That's one way of doing it. Yeah, so we could sort it as like an array where there's the notion of here's the priority, here's the actual element. And then if we choose to sort as we go, then we can have, here's the most important thing, or this visual isn't exactly clear. It's not clear to me what's the highest priority. I would maybe assume that it's 1, but this says rear, which typically I associate with the back of the line. So maybe 3 is the highest priority. If you implement this, you should say, what are you assuming is the higher priority? And so maybe this is the front of the line. And so in this case, either of these priority 3 items would get dequeued. So I would encourage you to maybe look at a combination of maybe you store it in an array or and also use maybe a node to represent or some sort of data structure to say, here's the data and here's the priority. So combine what you know of data structures and create something that you're going to use. This is an example of a priority queue where the contents are like the letters in terms of where they are in the alphabet is so the letter is both data and priority. Where something earlier, I know, I think max is the later letters in the alphabet. So like a higher number, a later in the alphabet is a higher priority. And so as you insert it, it goes through. So first, if we just insert P, and then we insert Q. When we insert E, so since Q is later, if we just leave it here, then when we go to remove the max, when we go to remove Q, we have to go searching for it, find it, and then remove it. That's if we store the contents in an unordered way. If we store the contents in an ordered way, then when we insert E, it gets stored all the way at the beginning. So that's a choice that your group has to make of how are we going to store this? Right. And so the idea is we're always looking for like what's the next highest priority thing that we need to take care of. So you can implement it with an unsorted array. You can implement it with a sorted array where as you go, as you insert and remove things, you maintain that sorted property. If you want, you could also use a balanced tree. So in the videos, my request is that my requirement is you don't use like predefined APIs. Like the goal is for you to implement it. If your project is priority queue, you could use the tree API to implement it. But if you're assigned a binary search tree, then you couldn't use the tree API. One option is you could have maybe you have an unsorted array, but you've got a pointer so that you always know where the minimum element is. And so that makes removing the minimum element or minimum like being the highest priority thing. And then that makes it easy to just remove that. And so the complexity differs based on how you implement it. So unsorted array, inserting is constant because you just stick it in there. Finding minimum, if you've got this pointer, then that's constant. Deleting the minimum would be linear because you know where it is, so you have it. But when you delete it, then you need to go through and find the next minimum. So remove, and then find the next one. And that's the bit that's order n. For sorting, using a sorted array, the reason the insert is linear is because you have to put it in the right place. And then once you've got that, then find and delete is constant. For balanced tree, insert and delete are height of the tree, log n. And then minimum is constant. Again, assuming that you know where the minimum is. Questions so far? Okay, so then the last thing is hashing. So a hashing is something that maps some key to an integer. And this is used for something in dictionaries that help you find it. So one of the things you'll see, at one point, I think I wanted to use like a list of something as a key in a Python dictionary, and it was like, no, you can't do this. It's an unhashable type. So this is what that means, hashing, where we can take some sort of data structure that we're given and hash it into a simple number. We can also take, you may see like, it's used in cryptography. There's hashing functions where you can take like some secret string, and then that converts to some number or combination of number and letters that is that string hashed. So it's compressed. And so then you can compare if two people have the same hash, then they've got the same secret string. It's used for dictionaries to help you find things. It's also used for cryptography. The basic idea is you've got some function. If your data is X, typically if you're, yeah, so there's an example. There's an example in the book where like my function is 2x plus 1 and I'm trying to hash integers. And so I just multiply the number by 2 and add 1. And that gives me like an initial number. And then you just modulate it by the size of your structure, typically an array. And so the idea is that once you compute the hashing function and then you modulate it, and the idea is that typically another number is not going to have the same hash. So you could put it in that spot, and in an ideal world, nothing will collide with it. No other number is going to have the same hash. Unfortunately, collisions are an issue. So you can have a hashing function that leads to two numbers having the same hash. And there's a few ways to resolve that. So the idea is you've got some plain text and then you've got some function, and that gives you the same text but hashed. And the idea is you don't know exactly what the function is, and so you can't go from the hashed text back. That's the idea, which is why it's used in cryptography. So yeah, so if you've got, I don't know what the hash function is in this hypothetical example, but there's a possibility that two keys can be hashed to the same value. And so the question is, this is a collision, and the question is, what can we do about it? One option is what we call chaining, which is where we combine an array and a linked list, where we've got the array, that's just our basic structure, and the index is going to be that function mod 10. So some function modulo the size of the array. And if you want to resolve collisions by chaining, then each array is associated with, each spot in the array is associated with a linked list where, so like 21 times 2, let's see, f of 21 is 42 plus 1, which is 43. 43 mod 10 is 3. So that's how 21 gets to be assigned at index 3. But 55 and 5 get hashed to the same value. They get hashed to 1. And so the way that we resolve this with chaining is to say each thing is just the start of a linked list. So like 0, nothing's hashed to it, so it's empty. But 1's got 2 things that hash to this value, so I just add them on one after the other in this linked list. This is chaining. And so the idea is if you're looking for something, maybe we're looking for 5, and we know it's supposed to be at hash 1, and so, oh, it's not 55, so it must be in the next one. That's one way of resolving collisions. Another common way is to use probing, which is where, in this case, I think 55 is, yeah, right. So first we inserted 5, and then we need to put 55 in. But they're hashed to the same value, and something's already there. Something got there first. So with probing, sequential probing or linear probing is we go to the next available spot and we say, okay, it's not available here, so I'm going to put it right next to it. Or in the case of 8 and 13, if 8 gets here first, 13 comes here, that's full. So we go to the next one, that's full. So we go to the next one and there's a spot, so we put it there. There's different ways of doing this. Some probing algorithms may skip elements, or there's additional math in saying, if it's full, I'm going to go to some equation later. If the hash table is sufficiently full. There's also, I'm just realizing that I neglected to put this in. There's yeah, man, sorry, I should have thought of this earlier. There's a function that we can write of how full the hash table is, and at what point do we need to open it up, like make a new table and copy everything over. I will do that and I'll present that next time. Yeah, so there's different ways that we can resolve collisions, and we need to know like how full is this table? Do we need to make a bigger one and copy everything over? Because when we do that, we can't necessarily just copy everything over as it is, because the modulo function is depending on how big the array that we're given is. So if we have a bigger array, then the hashing could change. Yeah, so this is probing again, where if we're trying to hash 44 and it gets to spot 5, something's here, and so you go, in this case, you would just go to 6 and put 44 here. If you were to hash some other number, then you would come here, and then here, and then here, and eventually put it here. So here's the complexities of those operations. So, did I write down what N and M means? No, I didn't. What does N and M mean? Let's see. N items. M buckets. So M is the size of the array. Okay, so for search, it's N over M. But in worst case, so that's for like if you're using probing and everywhere is full. And so then you have to go through the whole thing in order to find your item. So worst case is linear. Insertion for both is constant, deletion for both is constant. And again, you can kind of combine this with maybe a priority queue to see successor or predecessor. What's the next biggest or next smallest item that I'm looking for? And then similarly, maximum and minimum are doing kind of the same, similar things. I'll note that since some of these, all the 3 assigned data structures, the binary search tree, the priority queue, hashing, and dictionaries, they're kind of intermingled, right? They have similar functions, like you could use one to implement another. And so I encourage you to use that functionality. So if you're assigned a priority queue, maybe you use a dictionary, a hash table that has this functionality to get the job done. Or maybe you use a hash table to implement a binary search tree. So use the tools at your disposal. Okay, I think that's pretty much it for this. Again, next time I will add, I forget the exact term, but it's something like the load factor. So I'll come in next time with that. After we're done with this unit, we'll look at sorting, and then the next one is divide and conquer. I plan for both of these to also have video assignments. So if you have a strong feeling on how this video went, let me know, and I'm happy to take your feedback into account. Okay, so my plan is we've got 17 minutes. So the goal is to get into your groups and talk about maybe, first of all, share contact information and decide when and where you're going to meet outside of class. And then maybe spend the rest of your time talking about how are you going to start approaching this problem? When you're going to meet, how is it going to get done? All right, so I'll stop the recording and have the rest of the class time for that.